Hello, Professor. My name is Robert Spires. Here is my presentation number 2. You've already read the problem, so you don't need it read again. The first step that we are going to do is the energy equation so that we can relate states 1 to state 2 and get this solved. So that will be the initial pressure over rho g plus the initial velocity squared over 2g plus the height of the initial height plus the head rise due to the pump. This will be the actual head rise of the pump. Let me stop here and just say that the actual head rise of the pump will be equal to the ideal head rise of the pump minus the losses inside the pump. We don't have any information about the losses inside the pump or how to calculate those. Each pump will have various losses due to its design, but we're just going to simplify that down to the actual head loss of the pump using this term here, and that will be equal to the final conditions plus the total head losses of the entire system. This term HL here incorporates both the minor losses, which will come from the features of the system. In other applications, these will be connections or fittings, like a 90-degree elbow. Here we have a sharp-edged transition between the tank and the pump, and so that will come into account with the minor losses. And we also have major losses through the length of this pipe. Now, at the initial state, this will be atmospheric pressure along with this. So P1 and P2 are both 0 since they are open to the air. The velocity at 1 will be negligible compared to the velocity at 2. The water will be moving, but it will be a negligible velocity. V2 will not be negligible. Z1 is a height of 6 meters. However, Z2 will be our 0 height value. And the remaining terms are important. So let's rewrite this. We are given the head rise of the pump is equal to this equation here. So let's go ahead and solve for the head rise of the pump. Now let's focus on the losses, both minor and major. The total head loss given in this equation will be equal to the head losses, I'll call that minor, and the head losses major. The minor head losses will be due to the contraction, and in figure 8.26 in the textbook, that is given, it is shown that the loss coefficient for a sudden contraction is a function of area 2 over area 1, where this is area 1 and this is area 2. We do not know this specific area, but what we can say is A1 is much greater than A2. Therefore, we will approximate that to be 0, and at 0, KL of a sudden expansion is equal to 0.5. The overall head loss equation for a sharp-edged sudden contraction will be equal to KL V squared over 2G. And now we can move on to the major losses. The major losses are the losses as a result of the friction of the system over its length. and that equation is equal to F L over D V squared over 2G. Now, we have a term V2 here, and these terms are the velocity that is occurring along the length of the pipe and occurring prior to and after the contraction here. But we are given a equation in terms of the volumetric flow rate, and we will therefore we will set V2 as the average velocity due to the fact that the volumetric flow rate will be equal to the area times the velocity of the fluid. So we will set V2 equal to V, which represents the average velocity through this pipe. So let's rewrite the equation. Plus the head losses. And, well, this is actually a minus. All right, let's factor out these repeating terms here. Caught the minus that time. All right, and let's also input this value here given by the equation. Let's solve for Q. Q is equal to, or let's not solve for Q. Q is equal to the area times the velocity. If we solve for V, we can plug in V here and have the entire equation just in terms of Q. Therefore, V is equal to Q over A, where A is going to be equal to pi over 4 times the diameter squared. Diameter given in the equation, or in the problem, as 0.07 meters. We don't need to convert. Previously did this calculation. That will be 259.88 Q. So now we have V in terms of Q, and we will input that. We will replace V with Q in order to solve for Q. Actually, before we do that, we can consider this friction factor here. We know the length, we know the diameter. Let's go ahead and knock out this friction factor here. The friction factor is usually in terms of the Reynolds number and the roughness ratio. So if we don't know our velocity, how are we going to find our Reynolds number? It is given in the problem that the flow within the pipe is observed to be wholly or fully turbulent. If we look at the Moody diagram here, I don't know if you can read it, but completely turbulent regime is referring to this entire area here. So we see here that we have very high Reynolds numbers here, but outside of this area, we see these sloping lines, but inside of this area, we see very straight lines. Therefore, we can assume that if the system is fully turbulent, that the relative roughness will be directly correlated to the friction factor, irrespective of the Reynolds number. So let's figure out what the relative roughness is. I believe table 8.1 in the textbook lists the epsilon of cast iron to be 0.26 millimeters. This will vary with the different materials. It is a measurement of the roughness of the material. Smoother materials will have a lower epsilon, more coarse will have a higher epsilon. And this will be the main and sole contributor of what gets us to determine our frictional factor. So the roughness ratio, epsilon over the diameter, is equal to 0.26 millimeters divided by 0.07 times 10 to the negative 3 meters. This is right. This is converting to millimeters. Sorry, 0.03 or negative 3 millimeters, and that is going to be equal to, forgot to write it down, whoops, this is a plus, 0.26 over 0.07, 10 to the 3. That will give us 0.0037 for our roughness ratio, which we can come here. Here we have 0.002, 0.004. That looks to be almost an equal length there, so that's multiplying by 2, and then that's multiplying by 2. So if there is a gap of 1 there and a gap of 2 there, then 0.003 would be about on the low side of this, and we will estimate it to be about right there. Which will come out to be right here, and we can say that this is probably, that increased by 0.005, that increased by 0.005, so this would be roughly 0.25, 0.0025, so this could be 0.001, so let's just call this 0.027. No need to go too crazy with it. So from the Moody diagram, .027. Now we can actually input all of these terms here and get that squared away. So minus 2,000, rewriting this term here, or this equation here, minus 2,000 q squared is equal to 259.88 q quantity squared over 2g times 1 plus 0.05 our KL plus 0.027 times 2 meters over 0.07 meters. That will be 0.77 minus 6 meters, and then we subtracted this as well, so minus 20 meters. Okay. Just gonna add that up. 1 plus 0.05. Wait, is it point? No, it's just 0.5. 1 plus 0.5 plus 0.77. All right, let's knock that out. 2.77 divided by 2 times 9.81. That will be 0.144, no, 0.141. And let's square this and multiply it by that. That will give us 9522.8 q squared minus 26 equals negative 2000 q squared. Add 26, subtract or add the 2000. Divide that over. This looks wrong. All right, so we have a flow rate of 0.048 cubic meters per second. Okay, let's see if that turns out to be a correct value. Now that we have Q, B says show that the fully turbulent flow was correct. So if Q equals that, then V equals Q over A, which is equal to 0.048 meters cubed per second divided by A, which is 3.848 times 10 to the negative 3 meters squared. So our velocity is going to be equal to 13.65 meters per second. Okay, that makes me feel a little bit better about things. Okay, so now that we have the velocity, let's go ahead and look for the Reynolds number, which is equal to rho Vd over mu, which is 999, 13.65. 0.07 divided by 1.12 times 10 to the negative 3, I believe. And that's, leave those units off because I don't have them written down. Holy crap. We've got 852,271.875 for our Reynolds number. Let's go ahead and see if we are in the wholly turbulent regime, or wholly turbulent regime with this Reynolds number. This will be 8.5 times 10 to the 5th. Here we have 10 to the 5th. Here we have 8. Here we have our roughness ratio that we found earlier. And so, wow. Looks like we are in the wholly turbulent regime, and therefore the assumption that we made at the beginning stands. All right. Now on to the efficiency of the pump. The pump efficiency, like all or many efficiencies, I think that there's a different efficiency for like a refrigerator. where it doesn't make quite as, it's not the exact same positions on the ratio, but eta, which is the term for efficiency, is equal to what you want to get out over a perfect system, an ideal system, which is the power that was provided to the fluid over the amount of work that you had to put into it. So how much did you get out per how much you put in? I think that that's pretty intuitive. And so the power of the fluid is given by the equation rho g q HA, where HA is the head rise of the pump. HA is, did I solve for HA? Oh, HA is given by this equation here. So let's go ahead and 20 minus 2,000 q squared rho g. So this will actually be rho g 20q minus 2,000 q cubed, which will be 999 for the density times 9.81 for gravity times 20, and q here we have is 0.048, and that will be minus 2,000 0.048 quantity cubed, which means that the power that was given to the fluid is equal to 7.240 kilowatts. And now we can use this with the given 70% efficiency that we have in order to find the work that was put into the system. Oops. So rearranging these terms here, work of the shaft is equal to the power of the fluid divided by the efficiency, which is 7.240 kilowatts divided by 0.7. So we should be expecting a number that is higher because this pump is not perfect. All right, so that is going to be 10.34 kilowatts of power. A little extra message about the efficiency. If you ever get lost and you can't remember which one goes which, try both. And if you had to put in less power than you got out, you know that you're wrong. This equation, when you're just thinking about, I want over ideal, or is it perfect over how much I want, you are taking the amount that you got out and you are dividing it by a term less than 0 or less than 1, which means that you are going to have an increased amount of power that you had to put in, due to the fact that if this was a perfect pump, an ideal pump with 100% efficiency, this would be a 1, and you would get the same amount that you got out. You would put the same amount in that you got out. So just a little double check yourself intuitively. You put in more than you got out, and that's due to a 70% efficiency. So even if you forget the order, you'll still be able to get the answer just by logic. Thank you.